afternoon. Welcome to this week's Colloquium. It's a great pleasure to introduce today's speaker, Maryam Modjaz, who, after some growing up nearby, went to Berkeley and then Harvard, where she got her PhD with Bob Kirshner. She then went on to Berkeley as a Miller Fellow, and as of, I guess, a little bit over a year ago, she's now on the faculty at NYU in the middle of New York. And Maryam, throughout her career, has been working on things that go boom in the night, various explosive transients, and I think she will also talk to you about various forms of gamma ray bursts and supernovae and what they do to their habitat and what their habitat does for them.
Thank you, and thank you very much for the invitation. It's a real pleasure to be here. And it's going to turn down the lights a little bit. That'd be great, because I have a dark background. So thanks again for inviting me here, and I had already very nice conversations today during the day. So today I will tell you about two of nature's most powerful explosions from massive stars, supernova and gamma bursts. These are such powerful explosions that can be seen over very large cosmological distances. I'll be able to get mic'd up. Okay, thanks. Thanks. So, supernova and gamma bursts are nature's most powerful explosions from massive stars that can be seen over cosmological distances. But before we can fully exploit the power and potential of such explosions, we first have to find out what their stellar progenitors are and what the explosion conditions are that give rise to various kinds of death in massive stars. And that's what I call stellar forensics, the title of my talk and the title of my research projects, namely figuring out what the stars looked like before they exploded. Because like a forensics team, we only see the aftermath, we only see the explosion itself, the death, and have to deduce, like a forensics team, what star exploded and how it exploded. And what I will also argue today is by looking at the environments of these stellar explosions, around here where they see supernova and the well-known M51, that also might give very important clues about the progenitors of various kinds of stellar explosions. But before I start the story, let me take a second to acknowledge my stellar death detectives, my collaborators with whom I had the pleasure and privilege to work over the number of years at the CFA, Bob Kirshner, my former PhD advisor, and various other people at the CFA there, at UC Berkeley, Alex Filipenko and Josh Blubman, the big research group that they have there. Now I'm collaborating with the PALOMAR transient factory, which I will discuss in a little bit, which is one of these new transient surveys similar to PANSTARS that some people here might be acquainted with. And then at NYU now, I'm starting to have a fledgling group myself with Federica Bianco as a postdoc, Yutian Liu, and David Fierros. So the outline and the roadmap of my talk today is to start with a broad introduction, given that people have presumably different backgrounds. And I will, as I mentioned, hone on the question of what are the explosion conditions and progenitors for the potpourri of explosions we see and detect and have been finding also now with these new transient surveys. And the example I will give, given the short amount of time we have today, is specifically the supernova gamma burst connection. The fact is that long-duration gamma bursts, when they were observed nearby enough, always had a specific type of supernova associated with it. And I'll discuss it in the detail, these broadline type 1Cs. But there are many more supernovae that were seen without GRBs. So GRBs, these gamma bursts that are marked by the fact that they have relativistic jets, only accompany very small amount of stellar deaths. And the question I will discuss in detail is what are the specific conditions for giving rise to a gamma burst versus a normal supernova. And the path I will take will be looking at a sample of supernova with and without GRBs and looking at some of the physical observables that might determine the outcome of the stellar death. So could it be explosion geometry? Could it be that only very aspherical explosions give rise to gamma bursts, which makes sense in the sense that GRBs are very aspherical events marked by highly beamed jets. Could it be mass? Could it be that high mass stars only give rise preferentially to these extreme explosions? And the third part, metallicity. And usually metallicity is perhaps the trick question during lectures and talks. At the end of the talk, people ask, what about the impact of metallicity? But we will discuss that in detail today. And of course, binaries might be also important. More than perhaps 50% of all massive stars are seen in binaries. And that might also impact the outcome of the stellar death in terms of Roche-Loeb overflow or common envelope evolution. I will discuss that a little bit, but it's harder to observationally constrain the presence of binaries in supernova and gamma burst explosions. Then I will give a little bit of a discussion of the future, which is already the present, so to speak, given that a number of these great time domain surveys have already started. And I'm specifically very excited to be part of it, given that a number of surveys, such as the PALOMAR Transient Factory that I'm part of, as well as PANSTARS, and in the future, perhaps in 2020 or so, LSST is coming online to really find a large number of very intrinsic transients that might tell us things about the universe, as well as be very useful cosmological tools, possibly. So in terms of a background, we all know and love the fact that supernovae are very powerful stellar explosions. This is an image taken with the HST of type 1a, in this case, 94D, that shows very nicely the luminosity output in the optical of one star, of one dying star, that rivals or outshines the galaxy, its host galaxy, that consists of 10 to the 8 to 10 to the 9 stars. This is, of course, a little movie here to show you that supernovae are transients. They only last, in this case, only a couple of weeks, depending on, of course, the detector and the distance of these objects. But these are transient objects, typically, and have been typically searched for given cadences such of weeks. This is another example of a very interesting galaxy that hosted two supernovae, one that was discovered in 2007 and one that was discovered in 2008 in the same galaxy. And the story of such a discovery is very, very interesting. I won't have time to go into detail today, given the amount of time we have, but if you have questions or are curious, please feel free to ask me at the end. But this was a supernova that was discovered via the X-rays, not the optical light, but the X-ray light that we think came from shock breakout, when the shock that was launched during the core bounce reaches the edge, so to speak, of the star and breaks out. And for comparison, this is a Milky Way star in our own galaxy, and this is a galaxy that's around 60 megaparsecs away. Now, the energy release and the radiation that we see is actually the smallest amount of, in terms of percentage of the total energy release. So the radiation output over the light curve that we saw for most of the supernovas, 10 to 48 to 49 ergs, though there are now a number of overluminous supernovae observed that have radiation output that is similar to the kinetic energy that gets imparted to the surrounding of 10 to 51 ergs for most of the supernovae, both type 1As and core collapse. And of course, core collapse supernovae emit most of their energy in terms of neutrinos. These are neutrino factories, where most of the binding energy of the core that then is turned to neutron stars released via neutrinos. And we, of course, detected those from 87A, which is one of the hallmarks of supernova neutrino work that verifies our basic understanding of core collapse and neutrino release. Now, let me remind you a little bit about the supernova classification scheme, because it can be a little bit confusing, especially since there are an alarmingly large number of new types of supernovae. So basically, supernovae are characterized based on their spectra taken around maximum light. Supernovae that don't show hydrogen are called type 1s, that I've shown here, and type 2 supernovae are characterized by the fact that they do show hydrogen. And of course, the most famous type 1s are the type 1As that I'm sure you've heard of. Those are the cosmological distance indicators that people have used over many years to map the expansion history of the universe, and with which the acceleration of the universe was discovered in '98, for which both teams received the Nobel Prize in 2011 in physics. But I won't discuss those kinds of explosions. While they are very interesting, they only compose 21% of all kinds of explosions, and the rest of the supernova zoo consists of various kinds of massive stars that are more massive than around 8 solar masses and undergo core collapse during their death. The type 2 supernova are the most common ones amongst those. They're around 60%. They show strong hydrogen features that I've drawn here in blue. The 1b supernova don't show hydrogen, but they show helium, as I've marked here in green. The type 1cs are a little bit the rejects of the supernova classification scheme. Those are supernova that don't show hydrogen nor helium. Perhaps some silicon and might be confused with type 1as. So that's important to keep in mind when people deal with high Z type 1a redshift, high Z type 1a searches. And the type of supernova that has piqued a lot of interest in the last 15 years is the broadline type 1cs, that's shown here, where these kinds of supernova exhibit broad absorption lines, shown here in silicon, that are the only type of supernova connected with long-duration gamma bursts. So these broad lines indicate very large expansion velocities where a significant amount of material is moving at around 30,000 kilometers a second, so a tenth of the speed of light. And when people model the light curves and spectra of those explosions, they yield high kinetic energies, more like 10 to the 52 ergs versus the 10 to the 51 ergs for canonical core collapse supernova. And that's why some people in the literature have called them hypernovae. Go ahead.
So the defining spectral characteristics of all of these types remain throughout the light curve?
Yes, except these broadline type 1cs were at around 3 weeks after maximum, their line widths are very similar to those of type 1cs. So normal type 1cs here, so which is more like 10,000 kilometers a second. So actually one of my research areas that I won't discuss today is seeing is there bimodal distribution of these kinds of supernova, and of course you have to do that as a function of time because the supernova spectra change over time.
Another quick question.
Sure.
Roughly what fraction of all supernova are the broad SN1Cs?
Okay, very good question. The question was what's the percentage of broadline type 1Cs? That has not been fully determined yet. The one survey, the Lick Observatory Supernova Search, that has tried to do volumetric, to yield a volumetric supernova rate, had too few of those in their sample. So they're rare. They're perhaps, depending on the numbers, 10 to 30% of all type 1Cs. So, but because this value is model dependent, 10 to 52 ergs, some people use 1D models versus 3D models. Kanemoto and others have various models. I would not like to call them hypernovae, but really call them by the observables, which is broadline type 1C. It's a long, pronounced word, but it's more accurate given the observations we have, and because I'm German, I like compound words, so I will call them broadline type 1Cs for the rest of the talk. And the community does now too.
You taught them.
Yeah. Well, I mean, it's the case that every time we saw a gamma burst and we took a spectrum of all, 9 cases where we could do that, it was a broadline type 1C, but still the modelers argue about the kinetic energy that was imparted.
How often are they connected with GRBs, broad type 1Cs?
So that's another good question. I will discuss that later, but only around, out of the 70 broadline type 1Cs we know, only 9 of them are connected with gamma bursts. So it's a fraction. Now you have to worry about viewing angle effects, given that GRBs are beamed. So I'll discuss that in a second. So what are the physical systems we think give rise to those explosions? Of course, type 1As are due to white dwarfs, carbon-oxygen white dwarfs in some kind of binary system, either with a main sequence or a red supergiant companion, or they are due to mergers of 2 white dwarfs. That's still an outstanding question. Now, the rest of the other supernova types are due, as I mentioned, core collapse of massive stars. And so this is a cartoon of a pre-explosion massive star, where shown are the various envelopes before explosion and the various envelopes and shells of various elements that were produced during the successive stages of nuclear burning, going from helium, carbon, oxygen, there's also neon, silicon, and then the iron core. Now, of course, this is a simplification. It shows you a spherical star, but of course, massive stars rotate, so they oblate. The various layers are not as distinct as I've shown you because of convection and so forth, but the point is to show you the basic makeup of the outer envelopes before explosion and which kinds of supernova they might give rise to. So if this hydrogen or the star that still has its outermost hydrogen layer intact goes supernova, I think gives rise to type 2. If you have a stripped star that has been removed of its outermost hydrogen layer, but the next inner one is still present, the helium envelope, you will see a 1b. And the type 1cs we think are due to the most stripped stars, the most naked stars that have been somehow been removed of their both hydrogen and helium layers. And also the long gamma bursts are, we believe, due to those kinds of stars that in some cases then give rise to collimated jets. And only 1% of all stripped supernovae, so both 1Bs, 1Cs, and bonded type 1Cs give rise to long-duration gamma bursts. So these are really rare beasts, the gamma bursts. Now, what are the ways you can remove the outermost layers? There are basically two different scenarios. One where you have a single massive star, single Wolf-Rayet stars that have metallicity-dependent winds that then remove the outer envelopes, or perhaps also eruptions. Some people have suggested that. Or you have a lower mass helium star in a binary that has been removed of its outer envelope due to Roche lobe overflow onto the companion star. It's very important to distinguish between the two scenarios given the fact that they would come from different mass stars. These are very massive stars that would give rise to GRBs. These are lower mass stars that would give rise to GRBs, or also Brodmann type 1Cs or any kind of other stripped supernovae. Now, the direct study and the attempt to look at pre-explosion images, usually taken with HST, of the around 10 nearby 1Bs, 1Cs with which we can do that, has not yielded any conclusive detections of the pre-explosion progenitor star. Of course, this has been done very successfully for 87A, the supernova in the LMC, where people found a blue supergiant before explosion, as well as for all the other 10 or so type 2s, but this has not been successful for these stripped supernovae. So what I'm arguing is there's a need for this indirect study where we look at the environments of different kinds of supernova and gamma bursts and try to see if there are systematic trends, both in the stellar populations and the metallicity, that might tell us what kinds of stars give rise to different kinds of explosions. And as a side note, we're having an exploding zoo of various kinds of supernovae, with the advent of both the transient surveys that I discussed, as well as actually people paying attention to non-type 1a supernovae. So we've been finding these superluminous supernovae, where the radiation output is almost the same amount as the kinetic energy of 10 to the 51 ergs, and there are a number of different mechanisms people have been suggesting why that might be the case. This is a very interesting and emerging field of study. Then there are various other ones. You don't have to remember all the details, but the point is that there are all these other kinds of exotic, yet astrophysically interesting objects that people are finding. And in order to really explore the parameter space of this teeming universe of transients that's shown here, we need new kinds of surveys that really sample cadences, so sampling times that are interesting and have not done before. So this is a plot that shows you this decay time, so the time over which a transient changes, either the light curve width or the delta MPV parameter, as a function of luminosity. And there are various kinds of objects. You don't have to remember all the details, but the point is they're well-known ones, as well as theoretically predicted but not detected objects. And the classical supernova field has been here, where you see type 1A's, core-collapse supernovae. And that's been limited to this range because of the fact that the surveys have had these kinds of cadences that go between 10, 20 days to at most 100 days. But to really sample the whole parameter space, discovery space, we have to go to cadences that are lower than that and really sample the same part of the sky a number of times per night, which now PTF, pan stars are doing, and in the future LSST will do. And this is a plot that was taken from a 2009 paper. In the meantime, both using PTF and pan-stars, various people have filled in this parameter space. We have many more of these luminous supernovae. We have these weird calcium-rich transients. We have potential 0.1A explosions. So that's become a very emerging field in transient science. So I'll quickly switch to gamma bursts, since this is not the topic, but not the full main topic of my talk. So the gamma burst view we have is such that we have some kind of central engine. The collapsor model is a black hole with an accretion disk, or in the magnetar model, we have a magnetar that is able to somehow produce a collimated jet in which internal shocks give rise to the gamma ray burst itself, the burst of gamma rays that in this case, for these long duration gamma bursts, is longer than 2 seconds. And when now the jet interacts with the circumstellar medium, it gives rise to external shocks that produces a synchrotron afterglow that observers see both in the radio, X-rays, optical, and also gamma rays. So when people talk about gamma bursts, it's not only the burst that they discuss in gamma rays, but also the afterglow that lasts much longer and also ranges over a whole range in the electromagnetic spectrum. And so every time people looked at the afterglow of the GRB, and once the fireball had faded, when people took spectra, it was that of a boron type 1c. In all the cases, given this redshift range, where we would have enough signal to noise to detect the spectrum convincingly, or see the shape of the spectrum convincingly. So this is a plot from the smoking gun case, 03-29, where the spectrum afterglow after the GRB was subtracted looked similar to that of 19BW, which was the very first supernova GRB connection, but people discussed it as being a very peculiar one because it was a boron type 1c. Before that, before 98BW, people actually had not seen or paid attention to these boron type 1cs. But in this case, it was a really clear case. It was a cosmological GRB, and it was not only spatially and temporally coincident, but we saw the light of the GRB metamorph into that of a supernova, and more so even with 2006 AJ that I observed in 2006, where the spectrum 4 days after burst, over time, metamorphed into that of a boron type 1c. Well, there are very few in this redshift range. So GRBs are rare. The median redshift for swift GRBs are the redshift of 3. So all the ones that are nearby in this redshift range, people try to get a spectrum. And when there was enough signal to noise, they saw bumps and wiggles that were that of a supernova. They're just very rare. There's one case that looked like a long duration gamma burst, but people discuss if it's a short or a long duration burst, where no supernova light was seen. And so that's debated still. That's 06-06-14. So the conclusion is, in all the cases where we had enough signal to noise, it was always a boron type 1c that was associated with the gamma burst. And it's really the fingerprint of these kinds of supernovae. Now, for Joe's question earlier, there are many more boron type 1cs where no GRB was observed. And it's probably not due to viewing angle effects. They're probably not off-axis GRBs, because people have tried to look for those in those cases, in these boron type 1cs, and even off-axis GRBs where the jet is collimated, the jet decelerates over time and then becomes isotropic and emits in the radio. And people have not found radio emission from 1Cs, 1Bs, and some of the boron type 1Cs. So the point is, GRBs need special conditions. And what are they? So one caveat to keep in mind is some of the supernova gamma bursts that I will discuss for the remainder of my talk might be a different population of GRBs than the cosmological GRBs. They have lower luminosities, they're less beamed to opening angles of 30 to 80 versus 5 to 10. And perhaps because they have lower luminosities, and they're only visible in the local universe, they might be much more common than cosmological GRBs, 10 to 1,000 times, depending on what kind of beaming angle correction you assume. So what are the GRB progenitor models? In all cases, the various models evoke a rapidly rotating core. For the collapsar model, it envisions a single massive star, Wolf-Rayet star, that has a rapidly rotating core in which stellar materials get accreted onto the black hole via the very rapidly rotating accretion disk that then somehow produces a jet. And when it was first suggested as a candidate back in 93, before any of the supernova GRB connections by Woosley and collaborators, it was suggested that it had to be a 1b, 1c supernova if it was connected with deaths of massive stars. Beforehand, people actually thought of many, many other ways, many other theories of how you produce gamma bursts. And actually, the connection with supernova was debated because people could not imagine that the jet would be able to penetrate the hydrogen envelope that can be up to 1,000 solar radii. But Woosley and others suggested that these would be 1b, 1c supernova, meaning that the hydrogen envelope had to be somehow removed beforehand. And that's when the GRB jet that lasts for 2 to 10 to 15 seconds will be able to drill its way through the stellar core and the envelope, as shown here in these hydrodynamic simulations by Zhang and McFadden. So they showed that this relativistic jet is able to leave the star in those simulations if it is a compact star, if it doesn't have its hydrogen envelope intact. Now the other ones, the magnetar burst has been suggested, but again, they need a rapidly rotating core and some kind of binary. But in each case, these kinds of progenitors, if they should have high angular momentum content in the core, would have to be at low metallicity. Because at low metallicity, the mass loss due to metallicity-dependent winds is low, and therefore, if there's a connection between the envelope and the core, there will be less loss of angular momentum. So these various models have predicted or suggested that these should be low metallicity progenitors, but the point, of course, is to check that observationally. Now, you might wonder if there's low mass loss in order to retain its high angular momentum content, how do you get rid of the hydrogen and the helium, if not through metallicity-dependent winds? Well, in order to, as the Americans say, have your cake and eat it too, you need another mechanism to remove hydrogen and helium at low metallicity. So one way is to do it by what's called this chemical homogeneous evolution, where you have a rapidly rotating star that, due to meridional flows that are set up, is able to bring in the hydrogen from the envelope in and then burn it. And so that's one way to get rid of the hydrogen, or you have some kind of binary common envelope system that has been also proposed. So it's still very important to understand the GRBs versus the supernova progenitors, and that's important for a number of reasons. One is due to just basic stellar and high-energy astrophysics. We ideally would like to make a map of the supernova remnant that is left behind, black hole, neutron star, the death that the star underwent, and then the actual mass and composition of the star that it started out with. Another reason, of course, is that these sources are sources of gravitational waves, neutrinos, so we want to understand which sources give rise to those emissions, those kinds of emissions. And specifically, gamma bursts have been suggested as candidate sites for high-energy cosmic ray acceleration. Another reason is that core collapse, supernova, and GRBs have been suggested to produce and eject different kinds of heavy elements. So it's important, in order to trace the chemical enrichment history of the universe, to first understand which stars give rise to different explosions themselves. Also, GRBs have been suggested as candidate sites for R-process elements. And of course, the C word, cosmology. GRBs illuminate the very early universe that can be detected up to redshifts of 8 or 10, where the universe was only 530 or so million years old. But first, before we can use them to illuminate the early universe, we first have to understand which stars give rise to them, and also using them as tools, especially for indicating star formation over cosmological distances. We again have to understand which stars give rise to them in the first place. So let's talk not so much about explosion geometry, given the amount of time we have, but the main point is from a number of different lines of evidence, people have found, including my work in 2008, that asphericity is probably not the distinguishing factor between supernova with GRBs and those without. Even normal core collapse supernovas seem to have asphericities during the explosion. both from polarization measurements, other kinds of measurements, as well as core collapse simulations by a number of different groups. So let's talk about mass. Of course, mass is very hard to directly measure, given, as I said, the fact that we have had non-detections of supernova progenitors, and we can't use this method for GRBs because they're just at large distances, at these high redshifts. So what people do is try to gather evidence by looking at the environments. So this is a plot from Frucht et al. 2006 that shows this interesting plot where on the x-axis you have the fraction of light at the position of the explosion compared to the host galaxy, and the y-axis is a cumulative distribution itself. So if the explosion traces light linearly, you would expect the kind of explosion to trace this diagonal line, which is done by type 2s in this survey. So this is a survey that put together both gamma bursts that were observed by 2006, as well as type 2s that were found in the GOOD survey, where Adam Rees looked at the type 1as, and all the non-type 1as were given to Andy Fruchter. And in this plot, he shows that the long-duration gamma bursts are much more concentrated towards the brightest blue regions. This is in a specific band, in the blue band, of their host galaxies. And if you assume that that the light was emitted from massive young stars in the blue, the suggestion was made that long-duration gamma bursts prefer or come from more massive stars than type 2 supernovae. And that's corroborated by other kinds of detections, both the progenitor detections for type 2 supernova, as I mentioned, that has been done successfully with HST, and the masses lie between 7 to 18 solar masses, so a bit on the low end of the full massive star spectrum, versus long-duration gamma bursts, where more indirect modeling actually suggests that the masses are larger, perhaps 25 to 50 solar masses. However, I mentioned earlier, not any type of supernova is connected with gamma bursts. It's specifically the broader type 1Cs, or type 1Cs in this case. So what about doing this kind of analysis, specifically including type 1Cs? Well, that was done in 2008 by Kelly, Kirshner, and Parr. Here it's a very busy plot where you see different kinds of supernova and their distribution of host galaxy light. But the main point is that the 1Cs and the broadband type 1Cs here have the same distribution as long-duration gamma bursts, which is different from these other kinds of supernova, core collapse supernova, both type 2s and 1Bs. So the suggestion there, based on this paper, was that the local type 1C supernova and gamma bursts have similar locations compared to their host galaxy light, and imply similarly large progenitors for both kinds of explosions, both long-duration gamma bursts and 1C and broadband type 1Cs. And that perhaps an additional ingredient is needed for GRB production, which might be metallicity. So let's talk about the metallicity content of supernova with and without GRBs. So metallicity is predicted to not only impact the lives of stars, but also their deaths, because as I mentioned, due to the fact that different amount of iron has an impact on the amount of mass loss that the star undergoes, because the winds that people observe from massive stars, including Wolf-Rayet stars, are metallicity dependent. And if you have different amount of mass loss, there's also different amount of angular momentum content in the core, which is important for the various collapsor models. So this is a theoretical plot from Hager et al. And there's more recent work where Connor and Ott, showing you in this broad parameter space the outcomes of different kinds of stars with different kinds of progenitor masses and metallicity. Of course, again, this is a simplistic model, but this is just a motivation to see that there are different kinds of objects expected. 1Bs, type 2s, pulsational pair instability that gives rise to black holes and so forth, depending on these two values. So what do I mean when I say metallicity for the rest of my talk? Well, we observers actually refer usually to the oxygen abundance instead of iron abundance. And specifically here, I will talk about the oxygen abundance in H2 regions at the position of supernova and gamma bursts. They're usually in these funny units that are historically set. So why do we use oxygen? Well, it's the most abundant metal in the universe. It's weakly depleted onto grains because it's a dominant coolant besides hydrogen. There are very strong lines in the optical regime. And so people have worked on this area for the last 40, 50 years very intently. So there are well-established diagnostics that I will discuss, Curie-Dobita, Pitin-Pagel, McGough. Recently, Eva Grebel and collaborators had another paper in this series on discussing the various diagnostics. And I will show you also there are actually a lot of discrepancies, systematic offsets between the different diagnostics. Now, I will be measuring the oxygen abundance from H2 regions at the supernova site, where these H2 regions are produced by massive young stars. And given the short lifetimes of the supernova and GRB progenitors, we assume that the H2 region abundance is the natal abundance of the explosion, or of the progenitor before explosion. And given that these are short lifetimes, presumably the star didn't have much time to leave its birth site, which is actually different for type 1a supernova. So you can't use the same method, even though people do, for type 1as. So what is the state-of-the-art recipe for measuring oxygen abundances? So you have a supernova in a galaxy that went off. You wait till it fades and take your favorite large aperture telescope to go and take a spectrum at the position of the supernova GRB. And you want to do that at the position because there are large metallicity gradients in spiral galaxies going from metal-rich centers to metal-poor outskirts. And then you want to, of course, use the supernova that have secure IDs that are really broadline type 1Cs and not the 1B/C or something like that. Then you want to, of course, have a large wavelength range in order to determine robustly and uniformly the metallicity of the H2 region and correct for reddening correctly. You also want to remove the stellar absorption if there is any in the spectrum. And you also want to do a good job on the uncertainty budget. So actually, before I started in this field in 2008, people would show plots without any error bars. So when I started, I wanted to also improve that aspect and really propagate the uncertainties in the line flux measurements as well as extinction corrections into the metallicity determinations. And the last thing is we want to do this metallicity estimation in different and independent oxygen abundance diagnostics. So just to show you how important it is, this is a plot from Cooley and Ellison that uses Sloan star-forming galaxies using the same data, but plotting the metallicity-luminosity relationship in different diagnostics. And as you can see, even though the data are the same, the lines are similar, the relationship form and functional form is very different for different kinds of metallicity diagnostics. So it's very important to keep that in mind. Comparing values across metallicity diagnostics is very tricky, but if you stay within the same diagnostic, it should be fine. And if you see a trend in one metallicity diagnostic, you want to make sure you see the same kind of trend in other diagnostics too, meaning that it's a robust trend. And we also want to include supernova from galaxy unbiased surveys to mitigate selection effects, and I will show you why in a second. So the first hint that low metallicity might be important for GRB production observationally was in 2008. So let me explain this plot, since you will see various versions of this plot later on. So on the x-axis is the galaxy luminosity, where more luminous galaxies increase to the right. And on the y-axis, the oxygen abundance of the H2 regions at the position of the explosion in these funny units. In blue circles are all the broadline type 1Cs without GRBs, and red are all the supernova GRBs. And for comparison, I've also plotted the Sloan galaxies, the 53,000 star-forming galaxies in Sloan locally, in the same scale as everything else. And as you can see, in 2008, it seemed very obvious that there's this bimodal distribution of supernova with and without GRBs, such that supernova GRBs are in low metallicity environments. Now, the worry every time you see a trend is that could it be due to selection effects? And of course, there are selection effects for supernova surveys. So some of the local prolific supernova surveys, such as the Berkeley Lick Supernova Survey, has a very small field of view of only 7 by 7 arc minutes. So it has a list of galaxies that it targets every night, to find supernovae in them. But the list of galaxies consists mostly of high luminosity galaxies that have a lot of stars, such that the odds will be higher that one of them will go supernova. Now, the fact is that because these targeted surveys specifically target luminous galaxies, has also an effect on the metallicities in which you might find these supernovae. Because of the luminosity-metallicity relationship that I mentioned also earlier, more luminous galaxies are also more metal-rich. So if you only use supernova from targeted surveys, you might find only the supernova in more metal-rich environments versus gamma bursts that are found in untargeted surveys, such as SWIFT, which has a field of view that's almost 1/7 of the whole sky. So to mitigate those effects, in 2008 we included supernova from untargeted surveys that have this extra circle around them, and even those supernova found in the same fashion as gamma bursts, if they did not have a gamma burst, were in high metallicity environments. So in 2008, we tried to really compare apples to apples in a sense. Supernova broadland type 1Cs, not just any kind of supernova. We included supernova from untargeted surveys, and we did this comparison in the same scale. So we thought that the abundance offset is not due to selection effects. And the fact that in the future and already now, we have untargeted surveys is very important to find supernova and transients in all kinds of galactic environments, including low metallicity. So for comparison, the PTF, the Polymer Transient Factory that I'm part of, has a large field of view, 7.2 square degrees, no longer arc minutes, and can really cover the whole parameter space. Now, the next worry you have is, could it be just an effect of the diagnostic I used, Cooley and Dobbett 2002? So to mitigate that problem, we did the same analysis using different kinds of scales, Cooley and Dobbett, McGough, and Spitini and Pagel. And while the absolute values of the different oxygen abundances for the different supernova and gamma burst changes, the offset was still present between supernova with and supernova without GRBs. And so what are the reasons for the bimodal distribution that we thought in 2008 was in place? Well, one, as I mentioned, physically motivated is the fact that people have been suggesting that low metallicity stars would be very good candidates for producing gamma bursts. Now, recently, another supernova that did not have a GRB, but from radio observation indicated an engine-driven explosion has been found up here, as well as 2 other dark GRBs that are up here. So it's no longer a case that GRBs are exclusively in low metallicity environments, but they're still preferentially in low metallicity environments. So the next 2 suggestions in the meantime, since 2008, has been, could it be due to dust? Could it be that you only see the undistinguished GRBs, and therefore these GRBs have to be in low dust and therefore low metallicity environments? But what I would suggest there to counter it is that both kinds of supernova with GRBs and without GRBs were found in the same range of host luminosity. So if it's a dust content issue that might be related to the metallicity effect, then we would expect the same effect for both kinds of explosions. We don't see that. The last suggestion that people are making since 2010 is, could it be a star formation effect? Could it be because of the observed relationship between not only mass and metallicity, but also specific star formation rates, such that low mass, low metallicity galaxies have high specific star formation rates? GRBs are preferentially in these kinds of galaxies because these kinds of galaxies produce many more stars compared, or given their mass. So could it be that this low metallicity is not causation, but just a correlation? And of course, in astronomy, we always have to be very careful about that. If we see correlation, is it a causal connection, or is it just a byproduct of another correlation? So in 2011, Kuchevsky and West tried to test that suggestion. And we had another paper earlier than that with another data set, but I will show you this one, where we tested this suggestion. So this is the unweighted mass metallicity relationship for Sloan again, 53,000 star-forming galaxies that are plotted here, but not weighted by the star formation rate of those galaxies. If you then weight the bin points by the star formation rate, the metallicity luminosity relationship goes down. However, it's not as low as the GRB mass metallicity relationship that we and others have found. So this conclusion here was that the star formation weighting of these galaxies is not enough to explain the fact that the GRB host mass metallicity relationship is offset to such low metallicities. So another way to test this is to look at the mass metallicity relationship for other kinds of explosions that trace star formation, such as type 2 supernova or any other kind of supernova from massive stars. Because if it's a star formation effect, then it should affect all explosions from massive stars equally. So we looked at supernova from untargeted surveys, various different kinds of untargeted surveys. There are many of them. There's PTF, PAN-STARRS, the Cut in the Sky survey. There's going to be SkyMapper in the south. And we looked at the supernova from untargeted surveys, so again, different kinds, and compared them to both the Sloan mass metallicity relationship and those of GRBs, and found that the GRBs are still below the mass metallicity relationship of other kinds of explosions. So we suggested, and this is in prep, so we suggest and are suggesting that metallicity is a causal relationship. Because otherwise you would have expected all these other mass metallicity relationships for other stellar explosions to be also down here. But we can test this directly given the fact that these were small numbers and they're from various kinds of untargeted surveys that might have different selection effects. So part of my work right now with PTF is to measure the masses and metallicities of 85 stripped supernova from PTF, which is the same untargeted survey. And then recently, last week, exactly, yeah. So these 85 include 1Bs, 1Cs, and broadline type 1Cs. And we have around, out of those 85, there are around 17 or 20 that are broadline type 1Cs. So we do have good statistics on that. So this is data that, yeah, so these are already published data that do not include PDF. So these are published values given this range that had Sloan host galaxies. So Sloan measurements of the host galaxy metallicity.
So you just concluded or suggested from that plot that there's a causal connection between low metallicity and the long gamma reverse. If I look at the list of reasons, does that mean the top one, or does it still not distinguish between the top two options?
So I would say it excludes this third one. So we still have those top two ones. Yeah. And recently, just last week, there was another paper similar to ours in prep, but still different, that looked at a larger number of specifically broadline type 1Cs, so updating my plot with many more, both broadline type 1Cs and GRBs at higher redshifts too, and concluded that the GRBs are still preferentially in low metallicity environments, so with larger numbers. Now, of course, you can do this game for GRB hosts at many different redshifts. So far, I only discussed the low redshift sample, those that have an accompanied supernova, where we can detect them. That is only possible at low redshifts. But of course, you can do the GRB game at much higher redshifts. So at high redshift 0.3 to 1, I already showed a little bit this plot, but there it's important to keep in mind that the important emission lines are redshifted to the near-infrared, so H alpha, nitrogen 2, 7584 that you need is redshifted to the near-infrared, so you need a near-infrared spectroscopy to do this well, and Lavec et al. Did that in 2010. And again, here shown very nicely is the fact that even though there are GRBs at higher metallicities, the metallicity mass relationship for these GRBs are offset compared to the other kinds of star-forming galaxies at similar redshifts, both at low redshift and at high redshift. Now, at higher redshifts, going between 2 and 4, there's a different technique that people use, which is based on absorption spectroscopy in the GRB afterglow, similar to quasars. And there, it's again a different method. Usually people don't use oxygen because they don't see the absorption lines, but usually iron or magnesium or zinc. And there are other problems or interesting things to take care of. But even then, people, when they plot it, comparing it to other star-forming galaxies at the local similar redshifts, the GRBs are really probing low luminosity, low metallicity, and perhaps also more star-forming galaxies. So independent of the discussion we've had about what is the reason for this offset, the fact is that GRBs are sampling a new population or interesting population of galaxies that might otherwise not be detected in normal galaxy surveys. Okay, 5 minutes, thanks. And the metallicity field is really rapidly developing. There are many different other kinds of objects that I shortly discussed that people have been interested in, including parent stability supernova. The best candidate we have is 2007 Bi, which has been suggested to come from a very massive star, potentially POP3 star, that has actually only mildly low metallicity in this diagnostic. But in order to do a good job, we need larger samples for comparison as the next step. And so that's the next step I took a few years ago, when I was at Berkeley, to try to distinguish between not only the GRB progenitor scenarios, but those of stripped supernova. Because even for stripped supernova, the 1Bs, 1Cs, the question is it a Wolf-Rayet star that has been stripped of its outer envelope because of metallicity-dependent winds, or is it some kind of binary? And again, the statistical study that I've started is to look at the environments of 1Bs, 1Cs and see if there are specific trends as a function of supernova subtype. And there are different ways. So here is a similar plot where we observed 50 host galaxies of 1Bs, 1Cs and broad type 1Cs with Keck. So we had a statistically sample of other kinds of supernova too, the 1Bs, and 1Cs. I included supernova from both targeted and untargeted surveys back in 2008 to 2010. Now, of course, there are many more untargeted supernovae. Again, we took spectra of the nucleus and at the supernova position there. Keck's ADC, atmospheric dispersion corrector, is really great to do that. And we had a large wavelength range. And I tried to include really good job on uncertainty budget, or careful job at least, in including Monte Carlo simulations. So this is the result in this cumulative distribution plot where I've plotted oxygen abundance on the x-axis and y-axis, the cumulative fraction. So meaning that the fraction of supernova that have less or equal the value shown on the x-axis. And as you see, the type 1Cs are skewed towards more metal-rich environments. So these are oxygen abundance at the supernova position in both scales. Though, of course, the absolute values are different for the two scales. So I did a chromograph smear test to see if the 1Bs and 1Cs were drawn from the same parent distribution of metallicities, and found that's very unlikely, especially in this Bettini-Pagel diagnostic. And the important thing to remember is that it seems like these Brodmann type 1Cs without GRBs that are here in blue seem to be different from the type 1Cs. So this Brodmann type 1C business might not just be some kind of selection or viewing angle effect or something that is random, but it might be something interesting and inherent for this population of stars that give rise to these kinds of explosions. And there have been other papers out in the meantime. So as I said, it's a really booming field. Anderson et al. 2010 and Leludas et al. 2011 had other papers and other samples. So it's great to really put together the hard work of many different groups. And it was still the case with higher significance that the 1Cs have higher metallicities, or the environments of type 1Cs have higher metallicities than 1Bs. And so that's very interesting. It has a number of implications. One is that it's consistent with the Wolf-Rayet scenario, where type 1Cs have undergone more mass loss due to metallicity-dependent winds that are stronger in high metallicity environments. And the supernova types are really physically motivated. And there's been a discussion in the field, could the 1Bs and the 1Cs be the same kind of progenitor, but there's a different amount of nickel 56 mixing. And so here it looks like these are physically distinct populations. And this is the scenario we have given these two scales of a number of different kinds of supernova. The Broad M1Cs with GRB seem to prefer the lowest metallicity environments, then the Broad M1Cs without GRBs, then the 1Bs, and then the 1Cs. So we seem to have a sequence, given all the various work of different groups, and which is consistent with more indirect ways to estimate metallicity by Akavi et al. And Kelly and Kirshner. But recently there's been Sanders et al. Paper that suggests that there might be not a full distinction, given their sample, between the metallicity distributions of 1Cs versus 1Bs. So just to keep that in mind. So now I will, in the last 2 minutes, I will discuss very briefly some of these surveys that have been online and that what would be found with these surveys. So as I mentioned, PanSTARRS has been online for a number of years, PTF, the Polymer Transient Factory, and in both cases, these surveys use very large field of view cameras in a square degrees range, and therefore can discover transients independent of the host galaxy luminosity. So there's no metallicity bias in these supernova discoveries, as well as any other kind of supernova transient discovery. The other new feature is that they're searching for transients on many time scales, days, sometimes intra-night cadences, as well as weeks. And given these large numbers of surveys, we're really rapidly increasing the number of transients found, and specifically supernova. So we're having a doubling of the worldwide sample of supernova within 2 years, where before we needed 20 years. And of course, in the future, next generation will be the Large Synoptic Survey Telescope, which was ranked the #1 optical, #1 ground-based project in the decadal survey in the US in 2010. To give you a feeling for the scale, so this is the camera of the PTF survey, and in comparison, here's the moon. So it's a very, very large field of view with which it finds various kinds of transients. It uses, it's on the polymer 48-inch telescope, which is the Discovery engine, and we have other follow-up telescopes, such as the 60-inch that then takes multi-band light curves, as well as the P200, which takes spectra, because at the end you still need a spectroscopic confirmation of your transient to know which type it is. This is the PTF collaboration picture, which was taken in 2010, and the PTF consists of mainly these various institutions, including Columbia, where I was as a postdoc, and Caltech led, and the PI is Sri Kulkarni at Caltech. And we also use a large number of telescopes to follow up these explosions. Again, mostly to get spectra over time to see what type of beast it is, what kind of explosion it is. So we've found over 1,800 spectroscopically identified supernova, of which there are right now 86 supernova of 1Bs, 1C type, so these stripped supernova. And I'm working on, as I mentioned, to conduct a large host galaxy survey of these stripped supernova, which are all from the same single homogeneous and galaxy untargeted survey. Now, given the time we have, I will skip some of the interesting things we found, but I will go to some of the future plans. As I mentioned, with this large sample of 1Bs, 1Cs from PTF, I can check and construct the metallicity luminosity relationship for the transients from PTF to see where they fall. Are they similar to GRBs or local star-forming galaxies? To test if it's a physical effect, a la the collapsar model, or just a star formation effect. Other things we can do is, as I mentioned very briefly, we found all these other kinds of mysterious supernovae, such as the overluminous supernova, where the explosion origin is still debated, and perhaps host galaxy diagnostics might be a way to distinguish between the various progenitor models. Of course, many people are interested in explosions from POP3 stars at very low metallicities, so one step in that direction might be finding supernova locally in very low metallicity environments. And at least potentially, that's now possible with PTF and PanSTARRS. And we still have an unexplored parameter space. Is there a relationship between metallicity and supernova properties? And that would have large implications for example, deriving cosmologically important values such as supernova rates, because the metallicity changes as a function of cosmic age. And all these might be very important for understanding the implications of LSST, as well as guiding some of the selection effects or selection criteria for LSST. So here are my conclusions. So I mentioned from the beginning, one of the outstanding questions in time domain astronomy is what are the stellar progenitors and explosion conditions for the potpourri of supernova explosions we see. And the answer, and the example I gave is specifically the GRB supernova connection, where the long duration gamma bursts are only connected with broadline type 1Cs. And the implication for answering this question refer to a number of areas such as cosmology, the chemical enrichment history of the universe, as well as understanding cosmic rates of different kinds of explosions. And I've suggested that not explosion geometry nor progenitor mass, but the fact that the metallicity luminosity relationship for GRBs is offset to low metallicity might be a hint or suggestion for the key factor for producing nearby supernova gamma bursts. But one thing we have to keep in mind is the selection effects. Are we selecting based on star formation when we're finding explosions from massive stars or metallicity? Nevertheless, the metallicity field has become a really rapidly expanding area. The future is really fun, at least for me. We're starting really a really exciting, I would say, area or era of finding supernova and transients in an untargeted way from a variety of different kinds of surveys that might tell us more about the progenitors of these various kinds of explosions. Thanks.
Thank you very much, Maryam. We have time for a few questions.
So you showed a brightness versus cadence diagram.
Sorry, could you speak up?
You showed a brightness versus cadence diagram of various supernovae at the beginning of your talk. I was just curious where parent stability supernovae would fall on that diagram.
A good question. So the parent stability supernova have been suggested to be very luminous because they might produce a lot of nickel during the explosion, and they also would last a long time. So on the plot, they would be very luminous and very long lasting. But if you look at parent stability models themselves, and Dan here is an expert, there's still discussion how much nickel gets produced during the explosion. So initially, actually, Woosley and Norbert Langer suggested that only very little nickel gets produced, which is the powering source for supernova in general. So they would be very luminous and very long lasting.
So remind me again, I should no longer say hypernova, I should say
Yes.
broadline SN1C.
Yes.
Okay.
It depends what you're talking about. If you're talking about the supernova GRB connection observationally, that's really the case. Yeah, these are the broadline type 1Cs. However, when people model some of the supernova that might be produced during the explosion theoretically, and they see that they have high energies in the model, then it's still fine to call them hypernovae, because they're, by design, these are very energetic supernovae.
And how do they infer these large energies from 10 to the 52 up to even 3 or 4 times 10 to the 52? Is it?
Yes, so from the light curve, so the question was how do people infer these large values? So you still need to use both the spectra and the light curve to determine both the ejecta mass and the kinetic energy. So of course, just from basic one, kinetic energy is equal to 1/2 mv squared. That's what you see in terms of the kinetic energy when you look at spectral lines, but it's integrated over the various shells of mass. So there's a degeneracy if you have only spectra between kinetic energy and ejecta mass. However, if you look at the light curve, explosions that have large ejecta masses also have very broad light curves, because it just takes longer for the thermalized gamma rays to make it out, to diffuse out. Exactly, so for diffusion timescale. So then that's why you both need a light curve and the spectra to get to model the value of the kinetic energy that would have been imparted by this object.
So, assuming that the progenitors of GRBs are actually going on metallicity and the ones that they don't use, I think the theoretical idea, as you said, is that the lower metallicity ones don't lose as much angular momentum before they explode, therefore they're faster spinning. So the more direct reason that they produce GRBs is that they have higher angular momentum.
Yes.
Would there be a way of testing that more directly with the GRB progenitors are spinning faster?
So yeah, I mean, it's very hard to directly see the core, at the explosion. But there are suggestions, if people were be able to have gravitational signals from gravitational radiation, there's suggestion by Christian Ott that a highly spinning collapsar would have a different signature than a more spherical explosion. So if we had a nearby GRB, that's very unlikely, and we have advanced LIGO or perhaps LISA in the future, that might be one way to tell. Yeah, sure, of course, yeah.
So you expressed the excitement about the new imaging telescope, which I understand. Isn't much of what you're doing limited by lack of spectroscopy telescopes?
Yes. Yeah, so we have an avalanche of photometric candidates. So PTF is finding up to 1,000 supernova candidates per night or so. 100 to 1,000. And of course, we don't have enough spectroscopy follow-up to observe them all. So we have to make certain selections. And that's right now the bottleneck for both PTF and pan-stars.
But true enough, when people didn't have enough imaging telescopes, they built new imaging facilities. And I have not seen any effort to actually fix the lack of spectroscopy problem. I mean, down selecting,
Yes.
not
So
observing most objects is, of course, one reaction to it.
yes, but so now there is the next step. So there's PTF, intermediate PTF, that includes what's called an SED machine. So on the 60-inch that I showed earlier, there will be an IFU that will be able to have a GRISM of around RF 100, low resolution spectrum to tell, and taken from each, for most of the transients to see what kind of object you have. So that would be a low resolution spectrograph that would be able to observe most of the transients. But that's the bottleneck, and it will be even worse for LSST, so I fully agree on that part. And so now myself and others are trying to devise photometric classification schemes where, given you have a light curve and different bands, would you be able to distinguish between different supernova types, given that you don't have spectroscopy later on, most likely.
Then I would like to wind down the discussion.